Hey there, welcome back to our calculus lecture series. And we're going to be talking today about packet 28 on section 4.5 in our book on something that's called L'Hopital's rule. In particular, what we're going to be doing today is finding an easy way to compute limits of indeterminate forms using L'Hopital's rule. And I want to say some indeterminate forms, and some of them are not going to be treatable using this. But many of them are. It's one of the tools in the toolbox. I have one YouTube video on this topic in case you happen to like the Lightboard format better or a supplement. Before we talk about L'Hopital's rule, we need to talk about indeterminate forms because it's probably been a little while since we've done limits. And so I'd like to remind you that we're talking about the limit as x approaches a of f of x. That's indeterminate form if I have something like 0 over 0, infinity over infinity, infinity minus infinity, infinity to the 0 to the infinity, infinity to 0, 0 times infinity. There are all sorts of ways that whatever f of x is presents challenges to determining what the limit is if in fact it exists. So all these weird expressions here are what we call indeterminate forms, and in particular, they're troublesome because for all of those, I can't just evaluate and use the method of substitution as I really want to. I really want to be able to just plug it in, but oftentimes I can't. For some problems, we were doing like algebraic factor and cancel as a primary method. That was like canceling the common factor in polynomials. So this is an additional technique, not a replacement to the other techniques that we've learned previously. Let's turn the page. So L'Hopital's rule is the rule for ratios of functions that go to 0 or to infinity. That is to say, each of the functions goes to 0 or infinity, not the ratio itself. So in particular, we're going to suppose that I have f and g, and they've got to both be differentiable, containing a. That's my point of interest inside the limit in these expressions here, right? That's the place that x is going to on the x-axis, right? I've got my a value. This is the x-axis, and we're thinking about what happens to my function values. What are they doing? And that is about movement on the y-axis, wherever it happens to be going. So as we approach our point of interest on the x-axis, what happens along the y-axis? So in the particular case that I have an indeterminate form, and that's presented in here, these two things right here specify that I have indeterminate form, and the forms of the particular indeterminate forms that we're allowed to have when working with this are 0 over 0 or infinity over infinity, and these infinities can be either symbols. So it could be plus or minus infinity over infinity. Either one can have a plus or a minus, doesn't matter. And 0 over 0, these are what's allowed. So when I just try plugging in my a, I happen to get, either 0 over 0 or infinity over infinity. What do I do? Well, I could try factor and cancel. I could try some like trig substitutions, or we could try L'Hopital's rule. It says that if I take the ratio of the derivatives, right? I've got my primes here, f prime over g prime. If this thing happens to be some concrete value, or it goes to positive or negative infinity. That is to say that the limit exists. I can well describe the value of the limit. Then the limit of the original functions happens to be the ratio of the derivatives of them. I think that's really pretty cool. There's some really cool meaning in terms of like the rates at which these functions are going to the places that they're going, like how fast are f and g going to 0 or going to infinity relative to each other. That kind of is at the core of this, and I opted to not cover the motivation, but instead just focus on the method itself. Feel free to ask in class if you'd like motivation or understanding about how this actually works, because I have admittedly completely swept that under the rug in this presentation. So the thing that I want is this ratio it's ratio of functions, the limit as x approaches a of this ratio. And it says that the original limit is equal to the limit of the rates of change of those two things as a ratio. So I do have an important note, and we'll play with this a bit as we move forward, that the rule known as L'Hopital's rule only immediately applies to 0 over 0 and positive or negative infinity over infinity. Other forms require rewriting as a suitable fraction, and that often means something like, so e.g. is for example, rewrite something like infinity minus infinity as 0 over 0 by combining fractions. There are a bunch of different options. I can't tell you what to do in every single scenario. That's something that you've got to learn for yourself. But let's see how L'Hopital's rule is used, moving forward to some examples and techniques. So let's start with what I have numbered as example 1. We've got the limit as x approaches 2 of x cubed minus 8 over x to the fourth plus 2x minus 20. Fine, whatever. I see a limit, and the first thing that I'm going to do is try to substitute. I'm going to plug it in, and I'm going to get 2 cubed minus 8 over 2 to the fourth plus 2 times 2 minus 20. Up top, I have 8 minus 8, which is 0. 2 to the fourth is 16 plus 4, minus 20 over 0. No! So I tried to plug in, and what I observe, I have our friend indeterminate form. In particular, the 0 over 0, or infinity over infinity. Huzzah! So I saw indeterminate form. That means that L'Hopital's rule applies. Cool. So let's try using L'Hopital's rule. I've got in the top here something, let's call that F. In the bottom here, I have what we're going to call G. So L'Hopital's rule, which I'm going to invoke by name, says that this thing here is equal to the limit as x approaches 2 of f prime over g prime. I'm not doing the quotient rule because I'm not computing the derivative of this thing. I'm computing the limit of this thing as itself, okay? It's a big difference between those things. It's kind of a mediocre G. Let me try again. So that's the limit as x approaches 2 of 3x squared over 4x cubed plus 2. And now we're going to, we did a thing, and so we're going to try to substitute. Don't mind my misspelling there. And that's going to be equal to 3 times 2 squared over 4 times 3, 2 to the 3 plus 2 is 3 times 4 over 4 times 8 plus 2. 12 over 4 times 8 is 32, 34, 6 over 17. Groovy. This is, I'd like to point out at this point in time, this all right here is an alternative to, say, like polynomial long division, because we would cancel the common root algebraically. And you will get the exact same thing, assuming that I made no arithmetic mistakes as I did this, which is always possible. I'm not perfect. Assuming I made no mistakes, and we would do polynomial long division, the common root would cancel, and you would get 6 over 17 when you tried plugging into the result of that. Huzzah! Huzzah! Okay. Let's do a trig example. Alrighty. So we're approached with the limit. The limit is x approaches pi over 2 of a fraction. Cool. I'm going to first try to plug it in. I love plugging it in this. So I'm going to have cosine squared of pi over 2 over 1 minus sine of pi over 2. Sine of pi over 2 is the number 1. Cosine pi over 2 is the number 0. So this is equal to 0 over 0. And what do you know? I've got an indeterminate form. Of course you do. We're training you on how to do this. I'm not going to tell you the right method to use on every problem. That's up to you. There is an alternate way to do this one that screams in my face. It would just be to do some algebraic simplification with trigonometric functions. There's a common root, and you can cancel it. Not too bad. You do a Pythagorean substitution, cancel the 1 minus sign in the numerator and the denominator, and you're going to get, I expect the answer to this to be 2, based on my random guess. Okay. So I got this indeterminate form, and that implies that L'Hopital's rule is in effect. So by L'Hopital's rule, I am not being pedantic. I am being a good mathematician and invoking laws by names, theorems by names, just like lawyers have to cite the locations of the laws. They can't just make things up. I'm going to cite my laws by name in order to keep my readers engaged and reduce the overall burden on the consumer. So this is equal to the limit as x approaches pi over 2. And now I'm not taking the derivative of this expression. I'm taking the ratio of the derivatives. 2 times cosine of x times sine of x. And on the denominator, I'm going to have minus cosine of x. Yeah, I'm going to be off by a minus sign. I am. Yep, because it'd be... Okay. Did I make progress? I could try plugging in, and I'm still going to get 0 for 0. But check it out. I've got cosines here. And so that's equal to the limit as x approaches our friend pi over 2 times 2 times sine of x over minus 1. And I'm going to try plugging it in here. That's equal to 2 times 1 over minus 1 equals minus 2. I was off by a minus sign. Okay. Like, pretty straightforward. There are some key parts to this. There's, like, check it out. Like, first you got to do it. First you got to show that you can even use L'Hopital's rule, because if it doesn't apply, then it doesn't apply. And if you do this, then you're going to get the wrong thing. You're going to get garbage. So the first thing I got to do is be like, hey, yo, L'Hopital's rule applies, invoke L'Hopital's rule, and then do what L'Hopital's rule says that you should do. Time for another problem. This is an interesting one. I really like this problem. So if I just try plugging it in, I'm going to have 0 from the right times the natural log of 0 from the right. From the left, it's not defined, so it's important that it's from the right. That's the only reason I'm really doing this. Is equal to 0 times minus infinity. I'll put parens in there. That's an indeterminate form. But I don't have 0 over 0. Or infinity over infinity with a plus or minus. I don't care about the sign. So I can't apply L'Hopital. Okay, fine. What do I do? Okay, when you can't solve a problem, solve a different problem. So what I'm going to do is I'm going to rewrite this as the limit as x approaches 0 from the right of the natural log over x to the minus 1. And so I'm just going to push the x underneath and incur the minus sign to do that. And so now what I'm going to do is I'm going to try to plug it in. All right. So I'll try plugging it in. And so I'm going to have natural log of 0 from the right over 0 to the minus 1. And that's going to be minus infinity over infinity. Ooh. Indeterminate form. Yay, I have L'Hopital's rule. So this is equal to the limit as x approaches 0 from the right of 1 over x, because that's the derivative of natural log, over minus x to the minus 2. And now I'm going to try to plug in again. And I'm going to get 1 over 0 over minus 1 over 0 squared. Infinity over infinity. Am I hosed? No, we're totally not hosed. We're good to go. So I'm going to rewrite this as the limit as x approaches 0 plus of, let's write this, let's flip this minus power here, because I've got this minus power, so we're going to like bring that one up right there. I'll write this as x squared times x to the minus 1 equals the limit as x approaches 0 from the right of x. Huzzah, equals 0. Yes. 0. I love 0. I love this problem. This problem is so cool. So there are some pretty cool tricks right there. It's like this boop, boop, like put it down there and rewrite it. That was like trick number 1. Trick number 2, L'Hopital's rule to produce this expression. And then finally to be like, boop, and put that back upstairs and write it like that. So this is kind of like a sequence of like 3 insights and like things that you could try in other related problems in the future, right? So watch out for things like that. That is pretty good. The thing I just highlighted right there. This like flip up here is pretty awesome. And then L'Hopital's rule is the third thing. So there are 3 great things for you to try in this problem. Flipping the page. I like this next example because it shows that sometimes you can do L'Hopital's rule multiple times to get there. So the first thing I'm going to do when I approach the limit as x approaches 0 of e to the x minus 1 over cosine of x minus 1, I'm going to try to plug it in. And I'm going to get e to the 0 minus 1 over cosine of 0 minus 1. That's 1 minus 1 over 1 minus 1, 0 over 0. So I got to do something. I'm going to do L'Hopital's rule. L'Hopital's rule says that this is equal to the limit as x approaches 0 of e to the x minus 1 over minus sine of x. The derivative of that minus 1 is constant, 0. So this minus 1 right here came from that, right? Boop. It's the derivative. And now I'm going to try to plug it in. And I'm going to have e to the 0 minus 1 over minus 0. Oh, fine. All right, cool. But that's no problem because I still have indeterminate form. So L'Hopital's rule, we're going to do that again. So this problem is equal to the limit as x approaches 0 of e to the x. The derivative of the minus 1 is 0 minus cosine of x. That's 1 over minus 1. Minus 1. So multiple applications got me there. We can make it take an arbitrary number of applications. Let's see what happens here. Okay, so I've got this function here. The limit as x approaches 1 of x squared plus 1 over 2x plus 1. Okay, well, let's just do L'Hopital's rule to it. So this is equal to the limit as x approaches 1 of 2x over 2, and then I plug in and get 2 times 1 over 2 equals 1. Right? Right? Oh, what's that? I didn't check that I could do this before I did it. I just did it. Well, I don't have indeterminate form? Oh, come on. How do you know that? Oh, I'm supposed to plug it in to start with, not just start using tools. I got to check whether I have the right tool. Got to use the right tool for the right job. Step 1, plug it in. And if I plug it in, I'm going to have 1 squared plus 1 over 2 times 1 plus 1 equals 2 over 3. 2/3, that's not equal to 1, right? So all of this is total and utter garbage. Because you didn't check first, right? We got to check. You got to check first. All right, so let's go ahead and sum up what we learned. Limit problems. That's where this is applicable. We've checked out limit problems with indeterminate form, like 0 over 0 or infinity. Nope, that's an 8. Or infinity over infinity, right? Not 0 times infinity or others. Rewrite those. All right, so step 1, plug it in. Step 2, we're going to justify using L'Hopital's rule if in fact we're going to use it. Because maybe step 1 reveals that you don't have to. And then step 3, I think, might be do L'Hopital's rule. And that's that the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. We also observed some like cool algebraic tricks, right? And that's like x equals 1 over x to the minus 1. We saw that. That was pretty useful. Some like, like cancel when you can kind of stuff. But I think that was kind of the big algebraic trick that we touched on here. Yeah, so you can flip upside down to do that. So that's our last page for this packet. Just want to say thank you so much for watching, and we'll catch you at the next one. Later.